Just a minute, I'll just, yeah. So in the very first lecture, we saw an introduction to the course contents, the course outcomes, uh, and other such ISC components. Some ISC components were also discussed. So today what we'll do is we'll start with an introduction to the course. So we'll try to understand and acquaint ourselves with what exactly is soft computing. So today we'll be looking at the basic concepts of soft computing. So we'll start with the definition of computing. Then we'll see the terms hard computing and soft computing along with the characteristics of both. After that, we'll be looking at the different constituents of soft computing. Just we'll try to get an overview and the applications of soft computing. And finally, we'll have an introduction to classical sets before we actually start with the fuzzy sets unit. So let us start with the concept of computing. So what do you understand by the term computing? So the term computing actually comes into picture when we are having a set of inputs. We are given with a set of inputs and we need to compute the corresponding outputs for those inputs using some algorithm or some formal mechanism or some control action. Okay. So basically that mechanism or that algorithm or that control action is nothing but computing. So computing basically is something which will take us from this set of inputs to the output. So it is going to take you from inputs to the output. That is nothing but computing. So you see this as a term F. F is nothing but a mapping function from the input to the output. So, so when we talk about computing, what do we understand by the characteristics of computing? When I say computing, computing should provide a precise solution. The control action should be unambiguous and accurate. That means there should be a set of steps which are unambiguous. So like something like an algorithm. And computing basically when we think of this term computing, what comes into our mind is there is some mathematical formula involved, there is some mathematical model involved. So this is basically the concept of computing. So basically you have a set of inputs, you are going to compute the output based on a series of steps. These series of steps are finite, they are precise, and they are accurate so that you definitely get that output y. Okay. Now from this notion of computing actually, this term hard computing was coined by Lotfi Zadeh. Okay. This scientist. This term hard computing is derived from the term computing itself, because computing, as we know, is basically just using some mathematical formula to get from the input to the output. Okay. So hard computing, when we talk about computing, there are there is a classification. There are two types. One is a hard computing, that is that is the term that we know traditionally. Computing actually is nothing but hard computing. So a computing is hard computing if precise result is guaranteed The control action or the algorithm that is used is unambiguous, and the control action is formally defined. So it is hard computing. So it's basically the conventional type of computing which requires a precisely stated analytical model. And there are so many examples of hard computing that we have worked with already, like problem solving, numerical problem solving, or some algorithms like searching, sorting algorithms, greedy algorithms, dynamic programming. All these are examples of hard computing because there are a set of steps. There is an algorithm which is formally defined, which is going to take you from the inputs to the output. Okay, so the inputs are known and the outputs are not known. Okay, you are going to actually know the computation, that means the algorithm you're going to know. You know that algorithm which is going to take you from the input to the output. Okay, so basically this is how hard computing works. So you have your input, you have you you have your algorithm. The algorithm will compute the output for you. The algorithm will compute the output for you. Okay, so uh, when we talk about traditional computing, you have your set of inputs. You want to find out, for example, some particular number in a list. That is searching, right? A searching algorithm. There's a list given to you of numbers, 12, right? So this is a list of numbers given to you. You want to find a number. I want to find out whether 5 is there in this list or no. So I apply a searching algorithm. So what I do is, I know my algorithm is defined properly. So if I'm going to go for sequential search, right, linear search, my algorithm is defined. Okay, I know the set of inputs. I do not know whether this output is present or not. The output of this algorithm is yes or no. Okay, so I mean, I do not know the correct answer as of now. That is the typical characteristic of a hard computing problem. It is a deterministic algorithm that you're using. You know the steps, you know how to do it, you know how to solve the problem. Okay, you know the problem will lead to a solution. So that is a typical hard computing approach. Okay, so the mapping function is known. That is important. The mapping function is known, which is going to take you from the input to output, is known. Okay, so if you want to list down the characteristics of hard computing, then we can say that it is the conventional form of computing. It requires programs to be written following a certain algorithm, a certain formal procedure. It is deterministic and it uses two-valued logic. Okay, so deterministic, you know, it is definite. It's going to work in this fashion. It's going to give you some result, and it uses two-valued logic. So two-valued logic is a true or false logic, right? So it will give you either the element is present or it is not present, right? Even if you write the conditions, it will be always if else conditions, true value logic, right? It needs exact data to solve a particular problem. So whatever data is there, that data is exactly given to it. The solution or output of hard computing is precise. So the output is precise. Definitely you are going to say, for example, if we talk about the same example, that is a searching example, then that element is present or not. It will be given to you precisely. It will not be something like, okay, this element is 99% present in the list. The output is not something like that, right? The output is definite. It is present or it is not present, right? it uses crisp logic, binary logic, and numerical analysis. Okay, so these are the characteristics. It's firstly, it is the conventional form of computing, requires programs or algorithms or a formal procedure to be written. Okay, it is deterministic, requires two-valued logic. Okay, two-valued logic is also known as crisp or binary logic. It requires numerical analysis. It requires that exact data to solve the problem, and the solution or the output is precise. The term here, the key term here is precise. The solution, the output is precise. Okay, now let us try to understand the term soft computing with respect to hard computing. Okay, so soft computing is a collection of methodologies that aim to exploit the tolerance for imprecision and uncertainty to achieve tractability, robustness, and low solution cost. Okay, so the key words here are, they are going to, these computing techniques, soft computing techniques, will be exploiting the tolerance for imprecision. So given that the nature of a domain that we are going to work in is imprecise, the environment is having some level of uncertainty, these computing techniques exploit this very notion of uncertainty and imprecision in this environment and give you a solution and provide you with the solution to this problem, which is robust and which is low in cost. Okay, so that is a definition, the definition of soft computing. So you require computationally intelligent systems which will combine knowledge, techniques, and methodologies from various sources to solve the real world problems, which are more complex, imprecise, and uncertain to some extent, right? So imprecise, uncertain, complex. The real world problems that we deal with are more complex in nature. They're not very, very simple, where a hard computing technique will give you a good solution, right? So we need to intelligently exploit this imprecision and uncertainty which is present in such systems to solve the problems. So in the case of soft computing, the input and output examples are known. Okay, so x is known, y is known, and a function, that mapping function which maps the inputs to the outputs is approximated. Okay, so given a new input, the corresponding output can be approximated. So whenever a new input comes, the output for that particular input can be approximated based on the previous input output pairs. So that is essentially the idea of soft computing. So you know x, you know y for some part of it. You have a set of examples. You know x, you know y, and you try to find out this function. You do not know f of x. You do not know a set of steps to go from x to y. You do not know those set of steps to go from x to y. Okay, that is the very notion of soft computing. So there is not, you do not have some algorithm like a sorting algorithm or a searching algorithm which will directly give you, you know, you follow 1 2 3 4 5, will give you the answer. Oh, this is the answer, it's always precise. No, that is not the case. Okay, you will, when you go for a soft computing technique, you will have some algorithm, but that algorithm will be a generic algorithm. The algorithm is going to be a generic algorithm, okay, which can be used for solving problem A, which can be used for solving problem B, C, and so on. Okay, so for example, if you want to recognize a face, a person's face recognition, I do not have this kind of an algorithm 1, 2, 3, 4, 5 which will tell, okay, this is this person's face. First of all, I need to curate a data set of these faces with tags, labels, right? I have the face, person's face. This person is X1, X2, sorry, X3. I don't know. I have a list of persons in my data set. Which person is this person, right? I want to find out. So I cannot directly write an algorithm which will directly tell me. Okay. I need some kind of a classifier which will be some algorithm which will identify this person's face as this particular X3. This person is X3. Okay. So this person is X3, but with not with 100% guarantee. No, no, no. I say this person is X3 with probability 96%. This person is X2 also, X3 with probability 96%. This person is X2, maybe X2 with probability 20%. So then you use this notion of thresholding and then you say, okay, no, this person is definitely X3 because the probability with which this algorithm is predicting is 96%. Okay. So a soft computing technique which is going to identify or which is going to solve this real world problem is going to give you an imprecise solution. Okay. So that is the crux of soft computing. It works in an environment of impreciseness, of uncertainty, and it gives you a solution which is imprecise in nature. Okay. There is always certain approximation. The word is approximation. Okay. And the actually this approximation is borrowed from the way we work, human beings think, right? Always we are used to approximations. We say that, we do not precisely state facts. We are not used to precisely stating facts. We will not say that it is temperature is 35 degrees Celsius. We will say it is hot today, or you know it's cold today, whatever. We have that nature. So the way we think, actually soft computing techniques borrow this from human beings. Okay. So this is the concept of soft computing. So when we move on to the constituents, so what all are the techniques that are involved as part of soft computing techniques? So these are the techniques, that is neural networks, fuzzy set theory, and evolutionary algorithms. So let us quickly see each of these in short. Okay. Before that, since we had listed the characteristics of hard computing, let us also list down the characteristics of soft computing. Okay. Imprecision, approximation, and uncertainty tolerant, right? So these are the keywords. This is the first characteristic. They are model free. They can evolve their own models and programs. Okay. They are not specific to some mathematical model. There's no analytical model which is there, which they have to follow. You can apply one algorithm, classification algorithm, to n number of problem domains, right? They are very easily adaptable, I can say. They're stochastic and they use multi-valued logic such as fuzzy logic. So multi-valued logic is a characteristic of soft computing. Model-free, multi-valued, imprecise. They can deal with incomplete, uncertain, and noisy data. So if there is some noise involved in the data, soft computing techniques have they have evolved and they have known to predict good results over noisy data as well. So if there is some noise introduced in the uh, samples that you're trying to predict, they still give you robust results with noisy data as well. So allows parallel computations. So for example, neural network. So there are some, to make this whole thing fault tolerant, there is neural networks. So neural networks have some parallel computations which are going on, which take care of robustness. They can generate approximate output or solution. So they give you an approximate output or solution, as we saw in this face recognition example. Based on neural networks, fuzzy logic, and evolutionary computations. So all these three techniques, these are the heart of soft computing: fuzzy logic, neural networks, and evolutionary computations. Okay. So these are the characteristics of soft computing. So whenever you have to differentiate between hard computing and soft computing, you can think of the differentiation in terms of the characteristics. So let us look at the overview of these techniques one by one. To begin with, neural networks. Okay. So an artificial neural net is inspired by the biological nervous system. It tries to mimic the working of a human brain. You already know this. It's a revision. Okay. We know that artificial neural networks, they learn by examples the way humans learn by their experiences. So modeled along the human brain, learning by example, and analogous to how humans learn by their experience. Data classification, pattern reorganization, data clustering are examples where neural networks are used. And if you want to look at a long list, this is the list of applications. Forecasting and prediction, that is weather, finance, stock market, disease prediction. Image processing, detection, classification, creating like images, compression, augmentation. So different domains, this is just listing out. Healthcare domain, prediction, mood detection. Natural language processing, neural networks find a wide variety of applications here in this domain. Text summarization, sentiment analysis, question answering, chatbots, question generation, and many more, right? So many of these applications you might have worked with in your minor projects as well, and maybe in some some in machine learning lab as well. Okay, but in this course we are going to look at more in detail the mathematics involved uh, in the design of neural networks. Okay. So when uh, we talk about neural networks, this is a very typical example of a neural network, that is handwritten character recognition. So handwritten character recognition basically it comes into picture because, I mean, it's a very good example which we can give for a neural network, is because people have different types of handwriting. Handwriting varies, right? Handwriting varies, and you know, people have different styles of writing the same letter or character or number. Okay, so 4 4 I can write it in different fashions, right? Something like this. So neural networks are robust. So if you give this neural network with a sufficiently, so there's a neural network here which you design, which you are giving with a sufficiently large number of inputs, okay, large data set of inputs, then it is going to predict, it's going to recognize the output. What will be the output in this case? The input at the time of training will be uh, the actual character and the class number, right? So there'll be 10 classes. If I'm talking about only like handwritten character recognition, if I'm talking only in terms of digits, let us assume, let us simplify things. Let us make it that we have only the digit 0 to 9, right? So I want to recognize this digit 0 to 9. So I have 10 output classes, right? Each of this is a output class. This is output class 0, this is output class 1, and so on. Okay. So when you give a sufficiently large number of input output examples, so what you're going to provide to this network is training pairs basically. The neural network understands that this is, I mean, over a period of time, over a period of time, that is the training time, it understands that whenever a new similar example comes, this comes given to the network at the time of testing, it will predict it correctly as 4. This is some neural, this output is 4. It will predict it correctly as class 4. Okay, so it that is robustness. So how the robustness is achieved in neural network is, you are giving sufficiently large number of examples during training, and it is able to identify different handwritings. I mean, 4 written by different people in different ways, it is able to identify. So it is robust in that sense. But it is important that you provide with different variants of 4. I mean, when you're collecting that, data for training the network, it is important that you provide with very different types of samples, so that the neural network can approximate whenever a 4 is given to be 4, right? So it is important that you include samples from, so many different subjects, rather than having only for, 4 or 5 different subjects. You have hundreds of different people giving you samples of 4. Only then you will have different styles. Okay, so very important to, or central to the concept of soft computing is data. The data that you are going to give has to be varied. It has to have sufficient examples from every class that you're going to have in your system. Okay, you cannot just expect your neural network to perform good character recognition, handwritten character recognition, if you are just, giving samples which are very unique or from few people, which is not having much of variation. It's not going to give you good results. Okay, so when you're going for any project which involves neural network, make sure that you are going for some data set which is actually very advanced, which is collected in this fashion, which is curated in this fashion, like a benchmarking data set. Or when you are doing it yourself, you have to make sure that you're doing it in this fashion. Otherwise, the results will not be that great. Next, fuzzy systems. So fuzzy logic is an approach which is based on degrees of truth rather than the true or false Boolean logic that we know, right? So it was introduced by Lotfi Zadeh again. So he's the father of fuzzy logic, Lotfi Zadeh. Fuzzy logic will deal with imprecise, incomplete, and uncertain information. Again, because everything that it models is in terms of fuzzy sets, and fuzzy sets make use of fuzzy logic. And fuzzy logic is nothing but degrees of truth. It is not 1 0, it is between 0 and 1. That is what I told you in the last lecture as well. So, what are some examples of fuzzy logic? So, wherever there is some decision making involved to generate precise solutions, okay, you from certain or approximate information. So in that case, you go for fuzzy logic. So whenever there is some decision making involved in the real world, you can go for fuzzy logic. Facial pattern recognition, anti-skid braking systems, transmission systems, control of subway systems, unmanned helicopters, all these are also applications of fuzzy systems. Okay. Fuzzy systems have also been used in image processing, power engineering, other industrial automation, robotics, and optimization applications to certain extent as well. But the traditional applications of fuzzy systems were in control systems. When you're designing these controllers, these are the traditional applications of fuzzy systems. So very old application, interesting application of fuzzy systems is this uh, Sendai Subway, which was the world's, this series was the world's first train type to use fuzzy logic. Fuzzy logic was used to control the speed, and it was developed by Hitachi. Okay, it was very efficient. It was found that it was 10% more energy efficient than human controlled acceleration. So the control of the speed, so that is what I'm saying, in controller systems was the traditional application of fuzzy logic. Okay, fuzzy systems were typically used in control systems where it was much cheaper, I can say, to model using a fuzzy logic controller than a digital controller, than a PID controller. Okay, so here in fact in Japan, a lot of fuzzy logic has been used in many of their appliances, like uh, the air conditioners, washing machines, heaters, all these cooling heating system in houses, even in Europe and places like that. Fuzzy logic has been used for, wherever there's this control application, control based system involved, fuzzy logic replaced that, because it is more robust and it is easy to model. You just need to actually define a set of rules and use fuzzification and defuzzification. Once that is ready, once you're, you have that domain knowledge of the system, then it is very easy to design it and embed it into a chip. So that is why people go for fuzzy logic. One more application I have with me is, I'll just present it, which uses fuzzy logic. You can hear it. You can hear the video.
Yes, ma'am.
Yes.
girl. Hey, roller boy, oh, roller boy. He knows you know he's cool when he hears you say, I dig him. Just wanna be a roller boy who's a lucky boy.
Heard of this? Have you heard of this software?
No, ma'am.
So this software massive actually is behind the making of all these movies where there are lakhs of characters coming at the same time, like the Narnia and Lord of the Rings, Harry Potter, all these movies. Okay, so all these are simulation softwares which actually get these characters on the screen. But not only that, each of these characters which are there, they are responding uh, with respect to the environment that they are placed in by doing some action. Okay, someone is throwing a hand, someone is throwing some dagger or something like that. Okay, and actually, these actions, they different actions. All these are generated using fuzzy logic. Okay, using this notion of probabilistic reasoning to a certain extent, using fuzzy logic to a certain extent, what they have done is they have used fuzzy logic to their advantage, and at the same time different agents. So it's like an agent based system, that all these are multi agent systems. Actually, these are agents, right? Okay, and these each of these agents is responding in a different way to the environment. Okay, that is done with the help of fuzzy logic. So massive software has massively used fuzzy logic for doing this. Okay, and you have seen the result of this. So fuzzy logic has been used for such applications, and as well you can find so many such applications where, apart from the traditional applications which these soft computing techniques use to um, get this interesting things out and read about them, and you can use them to a certain extent in your projects as well. Last year round, one of the groups had used multi agent system and use fuzzy logic there to certain extent. So you can use these ideas in your projects as well. Moving back to the slides. Next is genetic algorithms. Genetic algorithms are basically search algorithms, heuristic search algorithms based on the idea of natural selection and genetics, as we know. And the basic techniques of the genetic algorithms is to simulate processes in natural systems necessary for evolution. Okay, So basically, whatever is there available in the natural counterpart of the genetic algorithm. So where it is drawing its inspiration from, it is drawing its inspiration from genetics, natural genetics. So that same technique is employed in the artificial genetic algorithm. So in the genetic algorithm, the natural genetics uh, processes of mutation, of crossover, all that is borrowed here. Okay, and everything that you find there will be reassembled here as part of the genetic algorithm. So the genetic algorithm simulate the survival of the fittest among individuals over consecutive generations for solving a problem. So there'll be generations and generations. So we have already done one experiment on machine learning using genetic algorithms for solving problems, optimization problems. You must have used all these some library, right, in Python, which you could have all these built-in operations which were there, like mutation, crossover, different types of mutation, crossover, selection. Okay, each generation, each generation of the population is analogous to the chromosome that we see in the DNA. So the chromosome from the human body, from the DNA, it is brought into picture here, and everything is done around the manipulation of the chromosome itself. So chromosome, everything is a chromosome, is treated as a chromosome, an individual, and whatever manipulations are performed, that is the operations that are performed are nothing but mutations and crossover. Okay, and of course selection as well at the beginning. So basically, you're just exploiting what is known as a search space, and you're trying to find a possible solution. So that is the idea in genetic algorithms. Of course, we are going to revisit this again, and we'll see some interesting examples later on when we discuss genetic algorithms. Okay, so these the terms chromosomes, individual, these terms are interchangeable. They are used to describe the individual elements that the algorithm works with in each generation. Okay, and a collection of these individuals is also known as a population. The collection of individuals or chromosome is known as population, right? And then they undergo the process of evolution, that is application of these operations only. And what are the applications of genetic algorithms? The applications are traditionally optimization algorithms, optimization applications, where where you are going to search through a large search space. Search space is very complex. You want to find a solution, and in a short amount of time. The solution might be approximate, it might not be the optimal solution, because those problems may not be solved optimally in short amount of time. So you need to go for a genetic algorithm. Okay, so it's a search method only, it's a search strategy, but it is, you know how it works. It's where you do not know how the search space looks like, you go for genetic algorithm. It's largely unknown, it's very complex search space, then you go for genetic algorithm. It is simple, elegant, there's not lots of mathematics, it's simple mathematics involved in only the operations. It's very simple to write a genetic algorithm than to write an analytical solution for solving such problems. Okay, and solutions can be discovered, approximate solutions can be discovered which are close enough to optimal solution. Okay, so applications we have seen used in music generation, and what other applications you have used. They can also be used for some kind of uh, decision making, where you want to optimize something, you want to optimize your profits. Okay, And a very conventional example which we have seen is traveling salesperson's problem for genetic algorithm. You can use to find the shortest path, right? Wherever there is minimization, maximization, you can go for genetic algorithms. Next, uh, quickly, we'll just go through conventional sets, okay, and we'll stop. So, conventional sets are classical sets, that is a set with a crisp boundary. So, example is a set of real numbers, set A of real numbers greater than 6. How do you express it? The set of all x such that x is greater than 6. A is the set of all x such that x is greater than 6. Okay. Where there is a clear, unambiguous boundary 6 such that if x is greater than this number, x belongs to the set A, otherwise x does not belong to the set. So, what is the drawback of this kind of a set? This is a traditional definition of a set that we know, classical set, right? A set with a crisp boundary. What is the drawback of such a set? The drawback is that they do not reflect the nature of the human concepts and thoughts, which are abstract, imprecise, and ambiguous. Okay. For example, if you want to use this set, conventional set, to describe a tall person, set of tall people. Okay. So, tall people, you say height more than 6 feet. It could be subjective, from country to country, it will be different. Okay. But let us assume that you want to have this. So, more than 6 feet is tall. So, if I use conventional set, then this is the definition. The set of all x such that x is greater than 6, right? So, A is the set of tall people and x is the height. X is the height. Height is going to describe whether the person is tall or not. So, the problem is that such a set will classify a 6.001 feet tall person as tall, but a slightly person who is slightly missing that 6 mark is not tall, which is, intuitively it is unreasonable. So such a description is intuitively unreasonable because 5.999 hai, to why not tall, right? Missing the mark by 0.0001, right? So such a set is not actually able to uh, very well define what is there in the real world. A real world situation cannot be properly or well described or well established using a classical set. So that is the drawback of a classical set. Okay. So we will stop at this, and then in the next lecture we will continue with this discussion, and we'll look at the properties of classical sets, the operations, and then we'll move on to the definition of fuzzy sets. Okay. So I'll stop now.